Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to go over the fundamental theorem of calculus. So get ready to work with some definite integrals. Now, for the fundamental theorem of calculus, there's two different parts to it. The first part being that the derivative of some integral in terms of t, or in terms of some other variable other than what we're differentiating with respect to. So let's say some function of t dt, that's what we're integrating with respect to, but our bounds are from some constant of a to our variable we're taking the derivative with respect to x. So the derivative of the integral from some constant a to our variable x of our function f of t, well, that's going to be equal to f of x. Which, thinking about it, makes sense, right? Taking the derivative of an antiderivative should give us some form of our original function. And if we're going from a constant to our variable, well, then we're going to get f of x. The second part of the fundamental theorem of calculus says that if we're integrating from a to b our f of x with respect to x, so we're integrating some function from a to b, well, we're going to apply those bounds. So that's going to be equal to the antiderivative at b minus the antiderivative at a. So once we actually evaluate that function, we'll plug in b, and then we'll subtract plugging in a. So those are the two different parts of our fundamental theorem of calculus. And let's talk about how to actually apply them. We've learned how to evaluate indefinite integrals using basic integration rules as well as some integral properties. For example, how do we evaluate the integral of 5 dx? If we pull that 5 out in front, we're just integrating 1, which is going to give us our variable x. So this is going to be equivalent to 5x plus c. Don't forget that plus c because we don't have our bounds. Now remember, we actually estimated the area under the curve of our constant of 5 for the interval from 0 to 4, and that's when we were working with Riemann sums. Recall that we got the solution to be 20. Now because we were integrating a function that was a constant, that area was easy to calculate without actually doing the integral. The estimate was very accurate because it just was a box. We had to multiply length by height or length by width. So we got our area between f of x, which is 5, and our x-axis to be 20. But now we will find the solution by evaluating the integral by using the fundamental theorem of calculus. And we're going to use this part right here. So if I'm integrating, again, that same interval, we already know our solution's 20. Let's double check. So when I integrated this, remember I got 5x plus c. And we don't need to worry about our plus c anymore because think about it. If I have some lower bound and I have some upper bound, and when I integrate I get 5x plus c, when I take my upper bound of whatever that is, I'll plug in some x here, and when I subtract my lower bound, again, I'm going to be plugging in a different x. Here's my upper bound of b, here's my lower bound of a, that's going to get plugged into each of those. You can see that my c's will cancel out. So when we don't have bounds, we need the c, but when we do have bounds, that constant, whatever it is going to get canceled out when we subtract the antiderivative at b minus that antiderivative at a. So understanding that the c will not be applied here, we're just going to do, well, we integrated it to get 5x plus c, so we're going to have 5x, and we're going to plug in our upper bound of 4 and subtract plugging in our lower bound of 0. So this notation right here tells me that I'm still going to evaluate from 0 to 4. So I've already integrated, now I just need to plug my bounds into my new function, big F. So we can see up here I can do a shorthand of this. This is going to be f of x evaluated from a to b. That's just another way to write f of b minus f of a. So what I'm going to have is I'm going to have 5 times 4 minus 5 times 0. 5 times 4 is 20. Minus 5 times 0 is going to be minus 0. 20 minus 0 is indeed 20. So we get that same area that we got when we did Riemann sums, which was technically our estimate, but it was an accurate estimate because we were dealing with a constant. So let's now evaluate a couple examples working with that first part of our fundamental theorem of calculus. So in example 1, we're going to evaluate, starting with part A, the derivative with respect to x of the integral of t squared with respect to t from our bounds of 1 to x. You can see that 1 is indeed some constant of a, and we're going to our variable, which is x. So this is going to be equal to f of x, which f of x, if f of t was t squared, then we know f of x is x squared. So that's our solution for part A. And let's take a look at this, integrating with respect to t, plugging in those bounds, using the second part of our fundamental theorem of calculus, and then let's take the derivative. We're going to get the same exact result. I just want you to be able to see that so you can understand this theorem. I'm going to integrate t squared dt. Integrating t squared, that's going to become a t cubed over 3, and if I didn't have bounds, I'd have a plus c. However, because I do have bounds, I get t cubed over 3, and I'm going to evaluate that from 1 to x. Again, I am just integrating t squared dt with respect to t. That gave me t cubed over 3, and now I'm going to plug in my bounds and subtract. So I'm going to have x cubed over 3 minus 1/3. So this right here, x cubed over 3 minus 1/3 is the integral, but what I'm going to do is I'm going to then take that derivative with respect to x. So if I differentiate now, x cubed over 3 minus 1/3 with respect to x, look what's going to happen. 1/3 is a constant, so that goes to 0. Taking the derivative of x cubed over 3, bringing that 3 down in front, then decreasing my exponent by 1, I'll get 3x squared over 3, which is going to give me x squared, which is exactly what I got in part A by using that fundamental theorem. Let's move on to part B, except this time with part B, let's not do this double check, because it's actually a fairly difficult integral that we don't quite have the strategies to do yet. We're going to learn these strategies once we get into Calc 2 in order to integrate B. But because I'm taking the derivative of some function with respect to t, and my bounds are going from a constant to x, all I have to do is plug in x for my function. So this is going to give me the cube root of x to the 4th minus 5x plus 1. Now I want to make a note that we can set this up slightly differently by using our integral properties. For example, if we were given this where our bounds were switched and we were instead going from x up to some constant, doesn't matter what the constant is, I'll just go ahead and use 6 again, that is not what the definition says. We need to go from our lower bound of a constant to our upper bound of x. But how do we switch our bounds? There's an integral property for that. All we do is we can put a negative out in front. And when we put a negative out in front, we would also have to put a negative out in front after we apply that fundamental theorem. So just keep that in mind when dealing with integration. Now, let's move on to example 2, where we're going to be working with plugging in different bounds. So for part A, we're first going to evaluate the integral of 3x squared dx from 1 to 5. Integrating 3x squared, remember, power rule, I increase that exponent by 1 and then divide by my new exponent. And a little bit of constant multiple rule here as well, because I can pull that 3 right on out in front. So I'm going to get 3 times integrating x squared, that's going to be x cubed over 3. See how I added 1 to my exponent of 2, and then I divided by that new exponent, and this is going to be evaluated from 1 to 5. But look, my 3 cancels out, so 3x squared when integrated is x cubed. And I'm plugging in my bound 1 to 5. Starting with the upper bound, we're going to do 5 cubed, and then subtract the lower bound of 1 cubed. 5 cubed minus 1 cubed, we know that 5 cubed is 125, and we're subtracting 1 to give us 124. Let's move on to part B. In part B, we have 2y to the 1 over 3 plus 4 dy. So this I'm integrating with respect to y. So I can use the sum rule and split this up and individually integrate each of my terms. Integrating the first term by pulling that 2 out in front, y to the 1/3, I'm going to add 1 to that exponent, so that's going to be y to the 1/3 plus 3/3 becomes 4/3, and then I'll divide by that new exponent of 4/3. And then I'm going to add that 2, integrating 4, that becomes a 4y. Now I'm evaluating this entire function from my bounds of -2 to a +1. But let's simplify down before we do that. If I have 2 divided by 4/3, that's going to be 2 times 3/4 when I flip that fraction, because dividing by a fraction is the same as multiplying by its reciprocal, so I'll get 6/4 or 3/2. So I'm going to have 3/2 times y to the 4/3 plus 4y, and I'm evaluating this from -2 to 1. I also want to make a note that as opposed to keeping all of these terms together, when I do the sum rule and split this integral up, I can apply my bounds to my first term and evaluate that, and then I can also apply my bounds to my second integral, evaluate that, and then sum them together. I don't have to do it all at once, I can split it up. So I could have done this from -2 to 1 and then added it to 4y from -2 to 1. But I'll just leave it all as is since I'm already on this path. So what we're going to do is plug in our upper bound and subtract plugging in our lower bound. So we're going to get 3/2 times 1 to the 4/3 plus 4 times 1, and that entire function that is my big F of b, my capital F of 1, I'm going to then subtract 3/2 times -2 to the 4/3 plus 4 times -2. Now let's evaluate this. 1 to the 4/3 is 1 times 3/2 is going to give me 3/2. So I'll have 3/2 plus 4 minus 3/2 times -2 to the 4th is 16. So I'm going to take the cube root of 16, which 16 we know is 8 times 2, and if I'm taking the cube root of that, I can apply my cube root to 8 and then to 2. So this is going to be 2 cube root of 2 plus 4 times -2, which is a -8, so I'll subtract a +8. Now, as of right now, I can combine 4, and then I can combine -8. 4 minus a -8 is going to give me a +12, but I'm still adding 3/2, and then I'm subtracting 3/2 times 2 cube root of 2, which multiplying 3 by 2 is going to give me 6, so that's going to be subtracting 6 times the cube root of 2 all over 2. And why I didn't simplify down 6/2 is because I'm going to find a common denominator and write this as a single fraction. And by doing so, that common denominator is going to be 2. So rewriting 12 as 24/2, I'll be able to add everything together. So 24 plus 3 is going to give me 27. So my final solution is going to be 27 minus 6 times the cube root of 2 all over 2. And that's my solution for part B. Let's move on to part C. In part C, we're integrating 8 sine of x from pi to 0. So let's start by integrating this with respect to x. Remember, the integral of sine of x is a negative cosine of x, because when I take the derivative of negative cosine of x, I get a positive sine of x. So integrating this is going to be negative 8 cosine of x, and I'm evaluating that from pi to 0. Now, you may notice that pi, as our lower bound, is actually a greater value than our upper bound of 0. And that's okay. We're just going to plug in our upper bound and subtract plugging in our lower bound. So we're going to do negative 8 times the cosine of 0 minus a negative 8, so plus 8 times the cosine of pi. And what do we get? Well, negative 8 times the cosine of 0. Cosine of 0 gives us 1. Negative 8 times 1 is a negative 8, plus cosine of pi is going to be a negative 1. Negative 1 times 8 is also going to be a negative 8. So I have negative 8 plus negative 8, which is going to give me a negative 16 as my solution. Another way we could have evaluated this integral is, remember our integral properties. We can negate an integral in order to switch the bounds. What I'm going to do in this case is I'm going to negate my integral at the start and go from 0 to pi 8 sine of x dx. Well, we know how to integrate 8 sine of x. That was negative 8 cosine of x. But I have a negative out in front, so a negative out in front of a negative 8 cosine of x is going to leave me with a positive 8 cosine of x, and I'm evaluating that from 0 to pi. Now when I plug in my bounds, I'll get 8 cosine of pi minus 8 cosine of 0. Look what happens. Cosine of pi is a negative 1, so I'm going to get 8 times negative 1, which is negative 8, minus 8 times cosine of 0. Cosine of 0 is a positive 1, so that's going to be minus 8. That's going to give me a negative 16. I get the same exact result, regardless of whether I negated my integral in order to flip my bounds or whether I continued on. Just remember that however we set it up, we're going to do the upper bound minus our lower bound when we go to evaluate the integral. So continuing on to part D, our last example in this worksheet, we're going to integrate e to the x dx. What's the integral of e to the x? That is e to the x. So we're going to have e to the x evaluated from the ln of 2 to the ln of 3. Plugging in my upper bound, e to the ln of 3 minus, plugging in my lower bound, e to the ln of 2. Remember, e and ln, those functions are inverses of each other. So e to the x is the inverse of ln of x. Therefore, they will get canceled out to leave me with 3 minus 2, which equals 1. And there we have it. Those are just a couple of quick examples for applying the fundamental theorem of calculus. Continue on to the next video where we're going to learn a new integration strategy. But until then, good luck with your online learning.